Welcome to the physics video lecture. Once again, it is Physics 107B video lecture 21. We are working on radiation. And what we learned last time is it's the accelerated charges that produce electromagnetic fields that actually escape out to infinity. And we had set up the dipole, which was an accelerated charge, and we're going to go through the whole process of finding the potentials, the fields, and then we're going to get the pointing vector and the radiated power when all is said and done. So let me repeat what we had and set that up, and then we'll move through it. So we're doing the electric dipole radiation. Electric dipole, and we had set it up to oscillate along the z-axis, and we've got a dipole length d right here. Put over here what we had the charge oscillating just as the cosine of omega t, so there's the frequency, and we have this time-dependent dipole out of this p naught cos omega t z hat, so that's the vector. Yeah, and we can even write that q0d, that's the magnitude of the maximum, comes out of this. Good. So let's see, we have a point out here, and as we do in cases like this, we identify this polar angle with all three of these angles. So we're sufficiently far away. We had labeled, this is a y-axis, which we'll abandon. So we had r minus, r plus, and just the point r right here. And what our task is, we're going to find V, and then we're going to find A, then we're going to find the actual field, so we get potentials, vector potential, the fields, and then S, and then finally the power that's radiated. So yeah, this is a really important object here, and it'll be good that we've taken it through systematically and tried not to skip any steps. Okay, so where were we? We had already set up the potential for the charge at those two upper and lower points. So from the definition, we went to, so rho PR. From here we went to the two-point expression. So Q naught cos omega t minus r plus over c over r plus Q naught cos omega t minus r minus over c r minus. And we had started doing some approximations. I think this is about as far as we had gone. Approximations were going to be, and this is already implicit in the construction, so that d is of course much less than the distance we're away from there, but also that d is much less than any wavelength that's being emitted, and the wavelength is much less than r. So we'll make use of all of those. Good. So then we had these expressions here, and I'll write down what we had found. So next, r plus minus, which was the root, just law of cosines, minus plus r d cos theta plus d over 2 squared. So our first, the one approximation was just going to get rid of the d over 2 squared. And then the next approximation is to pull out power of r, at which point we have d over r, which is small, and we can do the square root approximation, 1 plus or minus something. So you have to go ahead and just write that down. So there was r1 minus or plus 1/2 of this d over r cos theta. And then if we're going to, we're going to have that up here, but for the denominator, we can have 1 over r plus minus, and that will be equal to the 1 over r, but then the 1 plus or minus 1/2 approximation can go back up into the numerator with a change of the sign. So instead of minus or plus, it's plus minus. So that's 1 plus minus 1/2 d over r cos theta. Okay. So this is up in the numerator now. And yeah, make sure you recognize those. Those are, of course, important basic approximation techniques. So now we're ready to put all of these things into these expressions here. Okay, we're ready to actually plug everything in, because we can have it inside the cosines as well as these things from the denominator there. Good. So without skipping too many, we're going to we're not going to skip anything. Okay, so I think this is approximately where we were last time. So next, is cosine omega t minus, actually this r plus minus c, we're going to have cosine omega t minus r over c plus minus omega d over 2r cos theta. That's all the argument. That's all the argument of the cosine. Okay, so this cosine theta inside this cosine right here, just from having applied this expression here, and that r plus minus. So now we have trig identities for the cosine, cosine of a plus or minus b, and we're going to make use of that. And I'll actually just go this is equality sign. I'll just write here trig identity. And continue this line right here. We have cos omega t minus r over c cos omega d over 2r cos theta. And then we have a plus minus here, so we'll have a minus plus sine of, sine of the same thing. So sine omega t minus r over c sine omega d 2r cos theta. Okay. That's all just replacing this up here. Or going to, that's what's going to replace those up there. Now we have another approximation in play, namely that this omega d over 2r is going to be much less than 1. Okay. Right, d is much less than r. So this is going to be much less than 1, and in the cosine we can replace it with a 1, right, from the cosine expansion. In the sine we can just pull it out. We can just pull it out of the sine and make that the first term of the sine expansion. So that so I will actually continue this here and say I'm using omega d cos theta hold it I lost the power of c. C goes in here. Okay. That was from the C right there. Okay. So I gotta make a correction here. To C. To C. Okay. Less than 1. I think I've got both of them there. Let's see. Okay, so with that being said, we've got the 1 here, the cosine, and we've got the argument just explicitly out of the sine. And so now we have approximately cos omega t minus r over c times 1 minus plus omega d over 2c, that's the, came out of right there, cos theta, and then sine of the argument, omega t minus r over c. So this is the result that we can finally take, these were the numerators, take into the expansion up here. So we've made, right, we've made a number of approximations, but they're all very controlled. Actually, I have everything on the board. I don't want to rewrite everything here. Okay, this is going to be up in the numerator. So I've got Q naught times this thing here, okay, times 1 over R, but times 1 plus or minus this expression in the numerator, so in both of those. So that makes it for a pretty long expression. but we have one more approximation to do. Yeah. So all the ingredients are there. This, for this here, we've got the minus on one side, the plus on the other. We have to multiply these times, this expression here with the plus, this one with the minus, and multiply the whole thing out. And what I will put up is gotta erase this right here. Okay, I'm going to skip that. I'm going to skip the step where I put everything up and multiply it out here. But this is what we end up with for theta and t. 1/4 pi epsilon naught q naught divided by r d cos theta. And it's actually not the final result, so we'll discuss this briefly. Cosine omega t minus r over c minus omega over c sine omega t minus r over c. Close parentheses. So we still have one more approximation, but yeah, we didn't drop, we had cancellations there that left us with this. And if you'll remember, we're taking the lowest inverse power of r. That's the only one that actually contributes to the radiation. So this term will actually be dropped as well, okay? Because the 1/r at great distances is going to be much, much smaller than the omega over c. So for the radiation, as we had seen before, we only keep the lowest inverse power of r, so that we drop this one compared to this one. You can also just say omega times r is much, much less than the speed of light c. But yeah, so we drop that, and then we're left with the final result, this here, multiplied by that. So let's go ahead and write that out. And that actually has a nice shape to it. Good. So finally, v r theta and t is equal to minus p0. I'm pulling out that, I'm substituting for my dipole moment. 4 pi epsilon naught c. I've got the cos theta over r, and I've got the sine omega t minus r over c. Okay, that's nice. So that's the scalar potential. The vector potential is going to be easier than this, and so I'll make shorter work of it. Hope to have both of them on the board at the same time. So yeah, that's what's left when we just keep the lowest inverse power of r. So there's our potential, and you can see we're ready to use the polar coordinates for the problem. Okay. We've got a polar angle, we have no phi, which is part of the thing, but yeah, this can be interpreted as polar coordinates. Okay, so let's send that up and do the vector potential next. And yeah, the vector potential is that integration, but we'll see we can just trivially take the integrand and multiply it by a length. So that'll be a little quicker than this one was. The vector potential so what did we have there? Its definition, u naught over 4 pi integral j r prime retarded time dt prime divided by r. We can actually pull the whole thing out and multiply by that length d that we had, because that's actually our current density is just along the length d of our dipole. So for that reason, it's pretty quick. We're just doing an integral from minus d over 2 to plus d over 2. So we'll just pull the integrand out, evaluate it at the origin. I'll just remind you guys. So here's our origin, here's our angle. We've got d over 2 minus d over 2. Okay, so we evaluate the integrand at the origin, multiply it by d, which is the length of that integral, and we're done. Okay. So for that reason, I can, just having said that, and maybe I'll put a word or two about that. This is what we get. A R and T, we'll have minus u naught over 4 pi. We'll have the E naught omega over R sine omega T minus R over C Z hat. Yeah, so just for the record, evaluate the integrand at z equals 0 multiply by d. Okay. And of course the direction of this integral is z hat. Okay, that's good. So is that complete? That we can work with. Oh, actually, let's put a note here. This was the current density, so we do have to say where this omega came from. So note on that, I of t was equal to dq dt in the z hat direction. Okay, like that. That was minus q naught omega sine omega t z hat, because we're at the origin. So I've got my minus sign out of that, I've got the omega, and p naught is q naught d. So everything's been taken care of there. And now we have to find the fields. Okay, I'll have to make some room, but we have the vector the scalar potential, the vector potential. Now we want to find the E and B fields. And in order to do that, we're going to, I didn't write it out explicitly, but we have the same situation here. We have R, T, yeah. So the the spherical polar coordinates are what we're going to use. So next, calculation of the fields. Okay. I'll erase these, but of course these are the two expressions I'm referring to the whole time. So, calculation of the fields. So let's remind ourselves, we've got E is equal to minus gradient of the scalar potential minus dA dt. And let me go right straight to writing what it's going to be, minus dV dr r hat. Okay, so now we're in the spherical polar coordinates world, minus 1 over r dV d theta theta hat minus 1 over r sine theta dV d phi phi hat minus dA dt. Now this one's going to go away. We don't have any phi dependence in our expression. These we have to evaluate. And I see we're going to also drop a 1 over r squared term. I'm going to go straight to, not quite straight to the result. So there's a number of things going on in this calculation. I'll just make note, use cos theta r hat minus sine theta theta hat is equal to z hat. Okay, so we make use of this identity, which is one that isn't necessarily right there in our memory, but when you're doing these derivatives here, right, you're doing in terms of r hat and theta hat, when you're doing the dA dt, it was your z hat, but you're going to get a really nice cancellation when you do these derivatives. I think that's the main tricky point. And we also use this and drop 1 over r squared terms, because again, they're not going to, they're going to die away. They're not going to be the radiation terms. There will be some terms of that type. And what we end up with is E equals minus u naught p naught omega squared over 4 pi sine theta over r cos omega t minus r over c theta hat. Okay, so that's an important result. The B field is going to be just as important. You make use of those, but we can already start to study this thing. I'll send this up here. I want to put the B field right under it so that we can ponder them. Okay. So there's our electric field. And the B field, which is the curl of A, let me see if I need to say anything in particular about that. field. So the curl of A, so B is equal to the curl of A. I don't see any real tricky points on that calculation. We really just have the A sub R component of it. Oh, okay, yeah. Well, yeah, actually we do. We do the similar transformation to up here because we've got the Z hat, which we can express in terms of R hat and theta hat. So yeah, the same thing goes into the calculation of B. Let's go ahead and write down what B is. B equals minus U naught E naught omega squared. We're really looking at the same thing. 4 pi C. Remember the B and the E are differ by a factor of C right there. And then the same thing. Sine theta divided by R cos omega E minus R over C. But this was theta hat. This now is phi hat. So we're in plane polar coordinates. We have these fields at a great distance away, the radiation fields. Maybe we'll draw a little picture of our scenario again. But you'll notice E and B, as had to be the case, are perpendicular to each other because we've got a theta hat and a phi hat. In fact, let's go ahead and draw what was going on here, right? This was our Z direction. We're out here somewhere. Theta, I'll put that point right there. We're measuring theta. We're at some great distance. And what do we have for the E field? Theta hat. So at this point here, think of theta hat would be pointing in that direction, and phi hat would be into the board. So we can already see that when we go to the pointing vector, E cross B, so E cross B, actually phi is going to be out of the board. Let's think about that. Into the board. Yeah, that's right. Into the board, E cross B is going to be pointing in the direction of R hat. Okay, so this will be theta hat, and then phi hat. I'm not going to draw, and then R hat will be that direction. Okay, so we've got these transverse waves. Right, so if we look at that direction, we've got the transverse waves, and the cross product, E cross B, is going to give us the direction R hat, going to be our pointing vector. Other thing I wanted to draw attention to is over R here. Is and this is really important, the angular dependence when theta is 0 or pi. Remember that's what I wanted to draw right here. We had we've got our dipole oscillating in that direction, okay. And the greatest power and field strength is going to be 90 degrees to that. So in the theta equals 0 and pi directions, we're getting exactly 0 field strength. And in the theta equals pi over 2, we're getting the strongest field strength. So if you go ahead and look at the theta equals pi over 2, you've just got a 1 right here. You've got this cosine over R, which we recognize, right? The cosine of that argument over R we recognize as that exam problem we had that was a solution of the wave equation, which of course had to be because we obtained these whole operations as a solution of the wave equation. Well, we see explicitly we could just reverse the order of the argument. That's no problem. It's still a cosine. It's almost exactly the cosine of that argument divided by r, which is the solution of the wave equation. So yeah, check your exam. That was one of those problems. So, anything else to say about this? Plenty to say about it. I'm going to consult the clock. Well, good. We have our fields. I'll put down a couple of these comments here, just for the record. If I can find them. Yeah. So we have E and D are perpendicular. Right, these are the generic properties of the electric and magnetic fields. It has to be the case of the waves, fields in the waves. Yeah. So next, you want to calculate S E cross B over mu naught. So 1 over mu naught E cross B, and again, the nice thing is we just have to take the cross product. We're just going to multiply all these expressions and take the cross product of theta hat cross phi hat. So theta hat cross phi hat is r hat, and squaring everything, get the 1 over mu naught. Noting that theta hat cross phi hat is r hat, so that's just going to give us a vector magnitude multiplied times r hat, which is in the direction as I just mentioned. So let's do that. Pointing vector S will turn into mu naught over C, E naught squared, omega squared, omega to the fourth, omega squared, both times, that's right. 16 pi squared sine squared theta divided by r squared. And we see when we integrate this over, at great distance r, that's going to be finite. That's what we had to have. Cosine squared omega e minus r over c, r hat. So there's the, it's going to be our energy flux. If we average it over one cycle, we can average the cosine squared over one cycle, and we get the 1/2. So we'll do that. So averaging over one cycle, cosine squared gives us 1/2. So we can get rid of that dependence right there. So we have the average of the pointing vector. It's still a vector, by the way. So mu naught p naught squared omega to the fourth, right, 2 there, omega to the fourth, 32 pi squared c sine squared theta over r squared. Still in the r hat direction. So what we're going to do is average this, or integrate this over all of space now, surface integral, and then that'll give us the power. Okay. Finally, power, we will integrate S magnitude, right? The r hat and the d area are going to be parallel vectors, so that'll get rid of that vector there. So it's just S d area. And all that we're really going to have is that sine squared theta. Well, let's go ahead and write that out. So we've got the mu naught P naught squared omega to the fourth 32 pi squared c. Now the integral, area integral, so we've got sine squared theta over r squared. Then we've got r squared sine theta d, not dr, d theta d phi. D phi. So I'm just going to discuss this thing. This is out for arbitrary large r. The r squared's canceled. The d phi gives us 2 pi. So 2 pi from the d phi integral. And then the sine cubed theta from 0 to pi gives us 4/3. Yeah, you can easily do that. Okay. The way I did it, I just wrote sine cubed was sine theta 1 minus cosine squared, chop chop, right? You get both of those integrals, and that's 4/3. So that'll give us the power. Which I will write down. We have the fields, and then this power expression, which is so important. So I'm going to leave us with power radiated. When all is said and done, that's the total power radiated, averaged over a cycle. U naught P naught squared omega to the fourth over 12 pi times c. Okay. I'm going to consult the clock once more. One more thing I want to discuss about this. Yeah. So there's the famous power radiated by a dipole. We already saw by studying the fields, and we see it in the pointing vector as well, that it's strongly direction dependent. It's, in the polar direction, there's very little, and then when theta is pi over 2, of course you get the maximum. But that's the total power radiated. Now I want to do one more thing with this, because we are going to skip some material, but I need an important result out of this. Let me consult my sources here. Yeah. So, yeah, let me do a little more of that. there's a 1/2 sticking in here because of the fact that we averaged this. So let's discuss oscillating dipole in more general terms. So oscillating dipole, we could have P of t is P0 cos omega t. And that means that P second derivative, if you look at this, we'll pull out minus omega squared, right? So minus omega squared P0 cos omega t. Then we can also talk about a single point charge. And for a single point charge, we're going to write P of t is equal to Q times D. Okay, where D is this vector, so now we have a single point charge oscillating back and forth. And then we can write P second derivative is just going to be Q D second derivative. But second derivative of this displacement is an acceleration. Okay. So Q A of t. Because what we can do is take these results into this expression here and take back that 1/2 that we had from taking the time average. We can get a very important result that we might not be able to get along the long route. So I want to do it right here. So we have these results here. We've got the omega squared from the second derivative. And you see we have a P0 omega squared, the quantity squared. So let me send this up so I have a little more room. So using our power formula, right, and that omega squared, P naught omega squared, that quantity squared, we can make a substitution as a Q squared A squared, okay, up there. So that's what we're going to do. Make a little room. Yeah, then if we don't get to the full calculation, we'll actually have the result that we want. So yes, we can make that substitution. Yes. So from the power formula, using these results 1 and 2, okay, and ignoring, because we're back to the time dependence, we're back to the time dependent expression, so we're going to take back that 1/2, okay, and not taking the time average. That's our argument. We get power radiated is mu naught. We'll have the Q squared A squared. Make sure I got that right here. Yeah, just Q squared A squared over 6 pi C. Q squared A squared over 6 pi C. Very important result, because what we're talking about here is the acceleration. Remember, the power the radiation was dependent on the accelerated charge. So we have this very basic situation again. A is a function of t, so that's the power radiated as a function of time. And you can see those substitutions come right back out of this formula here in a more general way. So, do I have the time dependence there? Yeah. This is really important. We're going to use this in the material that follows in this chapter. So in case we don't have time to do a very long derivation of this, we got it from here in a hop, skip, and a jump. So that's a good thing. Let's see, I'm going to end consulting the clock once more. Yeah. So let me write a homework assignment down. And we haven't gotten to everything. This is for the chapter 11. But after the next lecture, we'll have everything that we need to tackle these problems here. So we're looking at problems 13, 14, 17, and 19. And 14 we're really more or less ready to tackle. These last two are going to require a whole section on radiation reaction. And so that's what we'll do next time. Very interesting topic in which we actually reach the limits of validity of classical electrodynamics and talk about that a bit and some unusual consequences of this formula. But good, so we made it here. This is the power radiated from the dipole. This is this generalization armor formula just for an accelerated charge. So A here is the acceleration. Let's put that in words. A equals A of t, the acceleration of the charge. So this is the expression when you bring it back to a point charge that's accelerating and radiating. Okay, good. We'll leave it at that. See you guys next time.